I happen to have one here on staff. That's your job.
We're going to quickly present our platforms, maybe a bit more in depth than yesterday. And I'm going to start with the F110 platform. I've already shown the robot, so quickly going through.
Basically, what is F110?
Yeah, F110 is it's a community of people driving these 1/10 sized race cars. It's actually no longer called F110. It's called RoboRacer. But if you check roboracer.ai, you'll find some information about it. There are a lot of these cars on the world, and everyone is different. So they're kind of open how to build them. There are also yearly races, and we also joined some of them. So it's quite a nice platform to test hands-on racing algorithms. It's built on a race car, Traxxas Slash. It's just an RC car, and there is a computer, LiDAR, some custom electronics, and very importantly, there is a roll cage. So that was very worth it. Yes, simulator is a very important part of it, and I tried to show the most important parts of it. So we, of course, have a simulated car, which is just a car model, and we have simulated sensors in a simulated 2D environment. And usually everything we develop in the simulation because that's ROS-free and it runs on everyone's computer without worrying about which Ubuntu version you have. And on the physical car, we have also some, these are ROS nodes. So there's a state estimation stack.
What is ROS?
A robot operating system. It's a
People
framework.
don't know what. Everybody knows what ROS is?
Yeah.
Okay.
Cool. Okay. Thank you. These are things that only a physical car can do. So the state estimation stack only exists on the physical car, as well as the mapping functionality and the actual sensors. And how we do it is we implement things in the simulator, and we initialize a car system from the simulator on the physical car, and we basically overwrite the simulated state with the actual state, and it keeps development kind of simple. So if you develop something in the simulation, you can just pull it on the car, and then it's already deployed. And I'm quickly going to tell you something about the state estimation stack and the controller, which are probably the most crucial things on this car. But for the limited time, I won't go too far into detail. So the state estimation stack starts with our sensors. We have a wheel encoder, IMU, the LiDAR. And the wheel encoder and the IMU, they deliver local odometry, which is a very high frequency, locally accurate information. So if the wheel turns once, we know that the car moved 30 centimeters. If the wheel moves 100 times, this information is no longer valid because it drifts over time, right? We can, same for the IMU, of course, that also is accurate in a local environment, but it drifts over time. We can even fuse this data with an extended Kalman filter, fuse the wheel encoder with the IMU, and this gives us the odometry. That's locally accurate state estimation. But for a global state estimation, we also need SLAM, which is simultaneous location and mapping. That is a sensor fusion from the IMU and the LiDAR. And on a known map, it can localize itself. On an unknown map, it can actually draw the map. And together with this information, we get our car state, which consists of position, yaw angle, yaw rate, velocity, and steering angle. You can guess that some of the states are very difficult to measure. We talked about this already. So the velocity in y direction, we don't have actually a sensor for that, nor for the steering angle. So these are approximated. And I wanted to brag by showing how the car localizes in the room, but I did a mapping in the room next to here because I thought the presentation was there. This is what a map from the car looks like. And you can also see the arrow. This is how it localizes itself in the room.
What are those red dots? I don't see it. Yeah. What arrow? That's the car is there at that arrow?
Yeah, the purple arrow, it's very small. The red dots are the LiDAR scans. And you can see that the room is kind of cluttered. These are just the chairs that are distributed all around the room. and the LiDAR sees them, of course. And with this information of the walls and the chairs, you can localize itself. That's another example how it looks like in action. So you can again see the LiDAR scans that almost all the time align with the track walls, but you can definitely also see some offset.
Where are the LiDAR scans? I can't see them.
Yeah, it's not made for beamers.
Okay.
So yeah, if you were
You would see some green dots around the walls of the room. Like
yes,
they kind of should line up with the walls.
Yeah, you would see them. They're quite small though. Yeah, but you will see a lot of these when running the physical car. But first, before running the physical car, I would invite you to check out the simulator. I'll share this link in the WhatsApp group. And there is a tutorial on how to install it and how to run it. And when you run the simulator, this is what you should get. And in this example, so the basic settings is a very simple controller. And yeah, I invite you to download that and play around with it.
What is that yellow dot?
I'm going to talk about it.
Okay.
So, yeah, that's a pure pursuit controller. In the settings, settings.py, this is where you can play around. You see some things like map name and controller, and there is a lot of maps that we mapped from the real world. Some are from actual races, for example, the ICRA 2022. And we also implemented a lot of controllers, and the one I just showed was a controller called Pure Pursuit, which is very common controller in autonomous racing. And there are a lot of controllers you can try. Some of them are more complex, some of them are more easy. And this is a quick introduction of the most common controllers in F110. So we have follow the gap.
Can you create a map like hand?
Yes, you can. You can, but the chance of the car localizing itself afterwards is basically zero. So you cannot just draw a room and then drive with the car in it. What you can do in the simulator is you draw a map with paint.
Yeah.
And then you can generate the race line for them. So that works nicely. Usually I also, if I did mapping, I have an empty room here. I have an empty room and I can virtually draw a map with paint in the room and then drive on this virtual map with a physical car. That's how we usually drive. Yeah, you see this map here is mostly hand drawn, but there are some actual walls here. But for the simulator, you can draw any map, yes. Okay, so first controller I want to talk about is follow the gap. And this is the simplest autonomous driving controller. This is kind of the hello world of robotics. We have a LiDAR on the car, and that scans the environment. And you can see there's a gap here. So from one measurement to the next one, there is a big difference, which opens the gap. And somewhere here, that gap is closed again. And we can just aim in the center of the biggest gap that we find. And this makes your robot already drive autonomously around some obstacles. And if you have a closed racetrack with walls, you can even complete laps like that. It sounds very simple. It doesn't even require state estimation.
Question: what if there are no gaps? Like, what if there is no like walls or restrictions? Like,
yes,
would it still drive itself?
It can get stuck. I mean, that's just a basic principle. Usually, you select the speed on the width or the depth of the gap. And if there's no gap, then you should program it to stop, ideally, and maybe even turn around. But you can definitely get trapped with this algorithm.
They'll put in a dead end in a real racetrack. They'll put a dead end so that everybody just does this, gets stuck in the dead end.
Exactly.
Yeah.
To avoid the dead end and to do a little bit more planning, we have the Pure Pursuit controller. This is the one you saw in the simulation. That also explains the yellow dot. It's present here again. Pure Pursuit works the following. We have a state estimation and a given race line that we want to follow. And the car selects a point from the race line that it's on the look ahead distance circle. So it just looks ahead by, let's say, 1 meter, and then drives a curve going through that point. And you can imagine that when I drive now for the next time step, I get further and the look ahead point changes. And this is how the car would converge to the race line. And you can also play around with that. There are a lot of engineering tricks you can do. For example, selecting the look ahead distance. That's not trivial. When you're fast, you want the longer one. When you're slow, you might want the shorter one. You can play around with that. It's all implemented in simulator already. And I talked a lot about MPC, and I finally tried to illustrate what it is for the people that don't know on the next slide, actually. So model predictive controller is an advanced control technique that relies on a car model. And the input of the controller is a goal and a state. And the goal could be, for example, a race line to follow, the green line here. And then the car model will execute a control sequence. And that's giving us information of how will the car react. So that's the red line. For a random control sequence, the car will do this. And through a cost function, which might be the difference of the goal and the future states, we optimize to find the control sequence that results in a minimal cost. And this is quite a computationally heavy operation, usually, because it's a very high dimensional space you're working in. And after finding the optimal control sequence, you execute the first step and then repeat the whole thing. So that runs all the time. That gives you the implicit feedback control. Model is never perfect, so if we deviate from the race line, we do the whole computation again, and that's how we can apply corrective terms. And this is what it looks like in simulation. There are a lot of random control sequences, the red ones, and the orange one is the optimal one. And when I say optimal, I mean with respect to the cost function that we define. Can do highly nonlinear control when we have a nonlinear model. Optimization is more difficult though for nonlinear control. It's very computationally expensive and requires a car model.
How do you do the optimization to find the smart one? Just number multiple one and take the best one?
That's one way for an optimizer. Yeah, actually here, this is called MPPI optimizer. Model predictive path integral, which you try thousands and then you weight all of them and you average by the exponential cost. And that's how you get quite a simple algorithm to get pretty nice optimal control if you have a lot of computational power. The car is kind of limited, but MPPI with maybe 500 of these rollout trajectories runs nicely. So for every LiDAR scan, we just check, are we hitting this obstacle? And if we do that, the cost is very high. So the optimizer finds control sequences that avoid the obstacles too.
Yes, in the different rollouts, is it only about like different parameters that you use and then you check which parameters are best, or does it also include like uncertainty about your state estimate or your sensors or whatever?
That's a very good question. It's not the parameters are fixed in our case. I'm sure you can extend it to a set of parameters and an uncertainty, but in this case, it's only about the control sequence.
Great. So now back to the simpler robot, but I think still interesting. Here with real demo. Alex, could you challenge it?
Sure.
So that it's not just that I am pushing it in some particular way, but it's really managing it to recover from disturbances. You can see it's mirrored also on the laptop, and I would like to tell you today again a bit more why it's interesting and then what we offer you here for this workshop. But I guess before doing it, I still need to connect my presentation. Or is it?
You can just go on.
Okay, fantastic. So first thing, why it's really interesting. Two more things. Yesterday I was talking about balancing is an important problem, that it's very convenient robots to test algorithms. And now two more things to this testing. Two features which this robot has and which are important, interesting, challenging. First, it's under-actuated. What does it mean? Can you guess what does it mean that it's under-actuated? It's a bit of a dictionary from control.
Somebody who's not a control person, guess what underactivated means? Elaine.
What is that?
Yeah.
Any guess? Yeah.
We're getting less power.
That was always what Toby says that he was thinking at the beginning. But actually, Elena?
One control input, like you cannot control both horizontal and the vertical, but only with this. So with one actuator, you control both all the state.
Exactly. Yes. So you have only one motor which is sitting here on the side, and this motor can move this card right and left. Here and at the pole there's no actuation. There is no motor. There is only measurement on the angle. So actually you have to complete two tasks with only one control input. First you have to bring it up, and second you want to move it to a target position without letting it fall. Yes. So this is already first nice challenging feature of this robot. Second thing, which I think makes this robot super interesting, is, well, let's do it as a quiz. Let's imagine that I am this card pole robot. You have to imagine I am this pole, and now let's say that the pole is falling towards the window. How I need to move the card to keep the pole upright? Very good. I move something like this, and I keep it back upright. Now, more difficult question. I am again the card pole, and I want to move towards the window without letting the pole fall. How do I need to move the card?
You will have to lean to your side.
So with this side. So I move the card. So explain us. Yeah,
a little bit to this side, make it tilt, and then move this.
Exactly. So I have to move the card in the opposite direction I want to finally go. The pole is tilting this side, so it starts falling. And then I can quickly accelerate towards my target position to, again, keep it upright. Quite so interesting, because you can see that actually to reach my target, that is be at the window and keep my pole upright, I first need to make a move away from my target. Yes, I moved the card away from where I want to be, and I tilted the pole where actually my target is to keep it upright. Yeah, this is a nice example that actually to reach your final target, you have to first go away. So it requires some kind of planning, and this is another feature of this robot, which makes it so interesting as a test bench for control algorithms. Now, I will not talk here much about software. I invite you to come in the afternoon today, tomorrow, install the software and play with it. There are two pieces of software you can get. There is a simulator here, actually working just as mirror to this physical card pole, but this can also work just as a simulator to test the algorithm simulation to generate data. Also we have, as in the car, very tight integration with physical robots, so that the same controller you will deploy in simulation can be automatically uploaded for the physical car pole, and mostly works. There is still some simulation reality gap, so not every controller which works in simulation works on a physical card pole, but generally, as much as possible, we try to calibrate this simulation to adjust it towards this particular robot. Now, a word more about controllers we use now, moving towards this more neuromorphic or neuro-inspired direction. Like this is still
I forgot the slide. Don't worry.
yours. Yeah, so this is actually still video from the 2 years ago, Telluride. At that point, we still needed the computer to run the carpool. Now it can run either from the computer or from chip. Currently, it's running just from this CPU on the board. There are also implementation on FPGA, but this for another time. Here, quick look still for equations. Elena asked me to show it specifically. So you can see roughly how complex it is. It is not terrible. It is easier than car equations we use, but still enough to have nonlinearities. Toby always is giving this great example that actually if you move the car in the to the right when pole is upright, then the pole moves clockwise, and when the pole is downwards and you move the car in the same direction, the pole is moving anti-clockwise. So this is also very nice visualization that this signs will really change, and it's a nonlinear problem. Yeah, but now back to the controllers, how we control it, particularly also in this case. Florian was telling a great story about model predictive control. This is really important controller, can achieve a lot, but also usually requires a lot of computational power. Now, on small chip, you not necessarily have this power, and here where neural network can come to your rescue. Namely, what we can do is we can, this is not this computer, okay. We can use this model predictive control, computationally intensive model predictive control in simulation to generate a bunch of exemplary data, what this controller do, how this controller controls the carpool. And then we can use this data to, by supervised learning, teach a small multi-layer perceptron, for example, a small neural network to do exactly the same job as model predictive control does. And of course, it has advantages, disadvantages. Elena will for sure tell about we lose the guarantees of safety and so on. And that's true that it's generally more difficult to ensure that it will always work, like we have it in the case of model predictive control. But we gain usually a huge speed up with evaluating a neural network in comparison to model predictive control. Now, so we have this implementation of this always using the wrong computer. We have this implemented both in the software and on FPGA, on both robots, on the carpool and on the car. And this can be also your starting point to work with some other controllers, other algorithms, like, for example, spiking neural networks. Here, short video for the comparison. We have the MPC running from the computer at 50 Hertz. And here at 1 kilohertz, this neural controller running on FPGA, and we see that the performance of both is roughly the same. It seems that maybe due to this higher update control frequency, this neural controller trained based on this MPC is even a bit more stable. Now, last slide, last step, and I guess I'm yes.
Think it's more, why is it more stable?
Well, I mean, you probably need the charts to see it more clearly than on this video. Well, but the justification is that the faster you can update the control signal, the smoother is your control, the better you can control. And even if this neural network is imitating MPC, and in this sense is always probably a bit worse than the teacher, it can still do better because it can update so much more quickly than the MPC.
Great, nice.
That's a very short follow-up. What is your intuition why the neural network is actually faster than the MPC controller? Because the equations that you showed are very simple. So why is the neural network faster at approximately the same?
Yeah, it's not clear yet how the MPC is expensive.
Yeah, what is expensive for?
Well, imagine that the equations I shown you only allow you to progress to make the step prediction of your robot. If you get a control input where it will be after let's say 10 milliseconds, right? What MPC is doing is taking this model and is solving the optimization problem over let's say half a second, and finding the sequence of controls sequence of control which gets the best trajectory. And even if these equations are not so bad, you can imagine that you have to solve optimization problem which involve thousands evaluations of these equations, or even 100,000 if you want to have a good control. Depends also if you also use a gradient on top of it. If you just do it like Florian showed with this MPPI approach, when you need even more evaluation but no gradient, and this can very easily get expensive.
Yeah, so the neural network approximates the inverse solution, like it directly tries to estimate what the right.
Exactly, it's the neural network kind of for each state learns what would be the solution of this optimization problem with some interpolation in between with little data. Yes.
Quick question. Have you tried to, so one of the differences is you're running one on a processor and the other on an FPGA. Have you tried to accelerate the MPC algorithm on an FPGA?
We didn't. Like for sure it would be much faster. For sure it would be also much more difficult to implement on a FPGA. And I don't have data for it, but it seems kind of obvious to me that still solving the optimization problem, even on FPGA, will be more expensive than evaluating this neural network, which for the carpool is just 2 hidden layers, 32 neurons. So it's really tiny thing, which is enough to control the device. For car, it's a bit bigger, but still very small.
I mean, if you think about it, you know, doing the same optimization in the same state over and over and over again, it's really stupid. You know, if you've done the same thing before, just do it again, right? It's deterministic. Mm-hmm. Usually these MPC solvers are sometimes they're stochastic, right? Sometimes they do a kind of stochastic gradient descent, but you're doing the same optimization 50 times a second or 1,000 times a second. You know, sometimes it makes sense. Other times, yeah, if you have the time and the horsepower, like you're running a big chemical plant, you know, and the whole chemical plant's running at 1 hertz, and you can increase the production of the chemical plant by 1%, which is where MPC was developed for chemical process optimization back in the 1960s. It really made sense because chemical processes are extremely nonlinear, exponential in temperature, products of compounds and stuff like that. But you know, that extended now, and basically you're just doing the same optimization over and over again. Why not just let the neural network memorize that and do it for you? Yeah, so this has a long history in control, right? And it's not accepted. And maybe Joel can say something more about this. Basically, for big aircrafts and stuff like that, this neural network approach is definitely not accepted because you can't guarantee certain rejection of disturbances and safety guarantees.
There's one advantage of the MPC. The MPC is always looking ahead. Mm-hmm. And so in some sense, it's taking future information into account. Yeah. So it can be more efficient. My guess is actually, if Martin actually plotted out how much torque was being used by the neural network, it's probably using more.
Good. Am I granted one last slide?
But MPC is a good way to get training data, but as long as you have a good simulation model.
Okay, now coming to your adaptive question. How this carpool is actually running the adaptive control again with neural network, and how it changes the process. Now we just collect the data for different parameter variation. Here, it's a pole length. Here, in this case, it's actually not a pole length, but for the demonstration reason, is the offset on the vertical angle. But let's do first this. We have data with various pole lengths. We again collect the data with MPC with now this pole length, and then we train this time the recurrent neural network again to imitate this model predictive control, with this difference that this recurrent neural network does not know the true pole length. Now, can it work? Let's check it here, or we would check it if my laptop wouldn't die, but we can still do it probably. That's actually a nice proof that it is really running on the chip, that the battery died on the laptop and that this is still running. Can I ask you here again, as to help me? Now, what we will do, we will unscrew. Let me switch this off. I will unscrew the pole. You can see that I can take it away. This is the potentiometer screw, and now you can rotate it as you wish. You can just by hand rotate it. Okay, and put it back. Yeah, not to the end because it will like more. Yeah, right. Exactly. We just added some offset on at the angle, and we have not informed the computer, the chip, that we did it right. And let's see if it's still able to stabilize.
You know what the problem is? Like it might be that zero, what I thought was zero is like over here now. So it tries to balance it, you know.
We might have a very bad luck that it's just at the top is the dead angle of the potentiometer, but let's hope not. And yeah. So, can anybody tell me what's the mechanism behind it? And why do we need the RNN here and we cannot do it with just a dense neural network? Yes, please.
Because this is similar to the vestibular system when you wear those weird eyeglasses that distort the angle.
Good.
Right?
That's a good example.
That's amazing, yes.
And you can still learn that, but it takes a little time though.
Exactly, yes. And here actually this learning is coming from the RNN like still having the past trajectories, like because it again it only gets a current state at a time, but thanks to its memory, it remembers the past trajectory and can say, okay, this trajectory must belong to this angle being at this particular offset, and it can adjust the policy to control the carpal without explicitly estimating this angle offset. Okay, this much for this part. You can check more details in this paper. The slides are online, so you can look at it whenever you wish, or just come and discuss it. Well, and we are looking forward where you will take it from here and what other things you will try with this robots. Okay.
Guys, I'll move on because we have 8 minutes for me and Matthias. Okay, thank you. So, welcome to Neuromorphic Active Vision. So, guys, basically, I don't have to convince you about why I do neuromorphic, so you actually know it. Now, the point here is that everything starts from visual attention. So, I've done visual attention in my PhD, and just trying to understand what is visual attention, like what is really attracting our attention or us moving our eyes around the space is not easy because it's different from, we have many factors that plays into role. So here, these are my channels of information that I decided for my thesis, which is intensity and depth and motion. Intensity because it comes free from the cameras, depth because I want the robot at some point to interact with the objects next to it, and then motion because it's inherently interesting, right? Like it's based off the alertness. If I throw something at you, either catch it or you do obstacle avoidance. Okay. Now, this is my PhD, and these are the 3 channels. Now, everything starts with this nice proto-object model that come from Ernest Niebuhr and Ralph Etienne Cummins. Actually, this model comes from Ralph Etienne Cummins from 2014. I've done 2 different versions of the things. The intensity, one runs on GPUs, and this runs on Spinnaker. Rather, this is the depth channel. I've used a stereo matching model to do with disparity fraction. Is a Jörg Conrad model. Then I basically give the disparity information to the proto-object model. Then here, the disparity is higher when the object is closer. Therefore, the most important object here is the closest one. So somehow I gave some sort of task to the visual attention, or some sort of like, okay, we know where we want to look at, because otherwise here it will jump here and there. It's completely bottom up. Then here, the motion channel, it's something that probably you might have heard, is a spiking elementary motion detector. It came from Moritz Milde from many years ago, but basically it's the work of Elisabetta Kicka with the time difference encoder. So what it does here is to give you the direction of motion, and also encodes the speeds, thanks to the mean firing rate of the population. Okay, so let's go faster. Yes. So here, all of my models are running on ICAB, which is a creepy nice robot in IIT at the Italian Institute of Technology, which is the land of ICAB. So what the robot is doing here is fixating at infinity. So I had to make the problem simpler, right? So there's no vergence. So the robot is staring at infinity and is performing circular eye motions, so trying to kind of like fake microsaccades. And then here we are doing the intensity channel. Here we do the depth channel. And what I want to show you here is this one specifically. So in this, it will come, but here what we see is the intensity channel. And here what we see is the depth channel, okay? Now, here is fine. The attention, which is the red dot, is on the bottle, right? But now when I put another object, the attention keeps switching between the 2 objects, right? And this is not desirable if you want the robot at some point to go and catch it. So if you put the depth information and you say, okay, always go and grab the closest object, now you don't have that problem anymore because it's fixed on the closest object, okay? All of this run on real time on the robot, and this is the motion detector. I don't have a nice demo for this. It was running on Spinnaker, and I lost a little bit of my mental sanity. This is just a follow-up. It's just one of the last papers.
A question for the depth, like what if you have 2 objects
at the same depth? Yeah, like it will pinpoint again. Yeah, it will pinpoint again. So you need to build, that's why I was saying that at the start, that attention is driven by so many things that you need to go to behavioral robotics, right? You need to understand what you want to prioritize. Do you want to prioritize something that is moving faster, or do you want to prioritize something that is, flashing at you? That it's difficult, right? To understand exactly what you prioritize. So you decide a task for yourself, and then you try to implement it, okay? Okay, nice, fine. So just to give you a bit of information, like let's say a bit of a benchmark, this is basically me benchmarking against myself in my PhD. So the intensity channel is running on a GPU, 100 milliseconds. The depth channel is running again on a GPU, 170 milliseconds in latency, because I need to also extract the disparity information. But if I go fully spiking, then we have a significant drop, right? So here we have, in 16 milliseconds, I can give you a very good saliency map of the scene, so I can tell you what is salient in the scene in 16 milliseconds. Downside that you don't see here is that I need 6 Spinnaker boards, which is unfeasible if you want to do it on a real world scenario. The robot cannot carry on 6 version 5's old Spinnaker. Okay. Now, let's go to what I was trying to explain the other day, so the sensory motor contingency. So what we are actually doing in our life is following with our fovea I'm not going to say anything about foveation, I'm scared, but we try to put things in the fovea, right? Because in the fovea we have high resolution, right? So we are forced to move our eyes. So what we do is like a continual visual exploration on things. And here, one thing that I would like to challenge you to think about is what's the definition of an object? What is an object is actually, if actually what we are able to see most of the time is a characteristic of an object, unless the object is very far, far away. So it's unclear to me, and I'm trying to explore it. So what I'm doing here is trying to prove to you that if we collect different ROIs plus joins information of the pan and tilt motion, the sequences of sensory motor contingencies might classify that a cup is a cup and the book is.
What does that mean, a contingency? I don't know what that definition.
It's basically a relationship. It's just imagine a sequence of contingency, and it's basically a synonym of saying relationship. But anyway, what is doing there is just a collection of sensory information and motor information, just a collection. What they prove in that paper, they have a robot that is poking objects and then collecting this to sensorial and motor information. What they say is that, of course, the bigger the sequence in terms of time, the better you classify. So you will have more classes to classify at the end. So I'm trying to explore this for event-based. Yeah, this is my pipeline. But then, as I was saying yesterday, I kind of understood that my biggest problem was trying to understand how to move a pan and tilt unit, so how to really go fully active with event-based cameras, because this is actually the first problem. So I tried to solve this pipeline, which takes an input information from the spec. This is a DVS, and then you have the Dynapse CNN. At the moment, everything that I'm talking about is running on my N2 on my Mac. I'm again losing my sanity putting it into the Dynapse CNN because the input is 64 times 64, so it's very difficult, hard, but I'm doing it. So we have the events from the spec. The spec is 128 to 128 pixels, so it's quite small. But what I want to prove to you here is that we don't really need bigger resolution, resoluted cameras if you are active. So here we have this object motion sensitivity model I was talking about yesterday, and is basically based on 2 Gaussians. And what you're seeing here is basically how is a simplification of what is actually happening into the retina. So in the retina, we have bipolars. So imagine that these are the bipolar cells that you are seeing in the retina, right? Then what happens is that the organization of these cells basically happens in something like this. So you have the center that is connected with an excitatory connection to the ganglion. And then you have the periphery that is connected to some amacrine cells. And these amacrine cells are inhibiting the ganglion. So what happens here is, imagine you have all of these cells triggered at the very same time, then you will have the inhibition of the amacrine cells and the ganglion would not fire, right? But what does it mean into the visual field? Into the visual field, it means that you have all of the pixels triggered at the same time. Then again, what does that mean? That the eye is in motion, is ego motion, okay? So this is how the retina is trying to understand if this motion that we have locally is coherent or not. So the retina basically is doing contrasting motion. Do we have a
You have to stop now.
I don't know, but my name is Claire. I work in music neuroscience mostly. I'm a musician. My 6th word would be music. More music, EEG, decoding, machine learning, computer.
That's it. You have more than 6 words.
Computational modeling of music, let's say it this way. So yeah, so I wanted to give a tutorial about decoding the auditory brain that I think is going to be useful to a general audience. It is mostly about, the auditory stuff. But those techniques can be applied to other types of stimuli, as we can discuss. And so, it's going to be a bit about what type of signal we collect, how the pitfalls that we have, the sort of problems that we face, and then the sort of main technique we have to address these problems. So neurocoding refers to the way in which information, such as sensory input, motor plans, cognitive states, is represented by patterns of activity across neural populations in the brain. And so one can investigate how the brain transforms these input into neural activity. But inversely, one can attempt to infer or reconstruct stimuli, intention, or mental states from recorded neural activity, such as the one that we record here with EEG setup. And that's neural decoding. Trying this action of trying to infer stimuli, that's what we call neural decoding. So neural decoding can be about reconstructing stimuli, identifying mental states, like fatigue, for instance, focus, intentions as such when we are about to speak, attention as what we attend to in a multi-talker situation, emotions as in when we listen to music with different, emotional undertones, etc. Could be, as many as you want to imagine. And it's achieved by first collecting the relevant neural data that's going to be able to, allow us to find correlates and denoise the signal to try to get at this relevant signal. And so then applying, and here I put a slash because denoising, because anything that's related to EEG analysis is basically denoising, because EEG data is noise, and what you're trying to do is to denoise it to get to the relevant signal that's hidden in it. So a quick overview of what we're going to see today. We're going to see how to collect neural data and what sort of data it is really. The problem that we have with this signal to noise ratio that I just mentioned. We're going to have a quick review of the classic neural analysis approaches that has been developed over the past 50 years, basically, of research using EEG data, if not more ancient, because we're going to see EEG is very old as a technique. And then we're going to see three main decoding techniques and their applications that have been developed more recent years, and I would say over the past 10 years, 10 to 15 years or so. So the type of data that we are interested in is electrophysiological data. And here the relevant world is electric. And it's basically the electrical field that's generated by the activity of neurons. So the currents that are formed by synaptic events in dendrites of pyramidal neurons elicit electrical field that we can record with electrodes that we placed on the scalp. Note that we can also, under this umbrella of electrophysiological activity, there are other types of data that we can collect that we don't do it here in Telluride because this requires other types of setup, but that's essentially the same sort of thing in the sense that what you're collecting, what you're recording is directly either electrical activity or magnetic activity from the neurons. And so one that you may have heard of is MEG, magnetic encephalogram, which is basically instead of recording the electrical activity or the electrical field, you're recording the magnetic field, which is of course related to this electrical field, but has the advantage of being, well, it's a problem because it's much smaller, but it's also much more precise because it doesn't get distorted so much by going through all the tissues like the brain and the scalp and the skin. So to do that, you need a much bigger machine that's going to try to suppress all the electrical noise and magnetic noise around you. So you need a Faraday cage, basically, like an isolation. And that's why this is something that requires also to have the electrodes plunged in a very cold solution so that it can pick up on these very tiny signals. So these are setups that you find in big university, research university in neuroscience, and are quite different from EEG that's portable and cheap and that you can bring, like we have an EEG setup lab here that we set up in just a few days. Just another quick note is that another type of data that's very relevant that you will see and even hear discussed in this workshop is either ECOG data or SEEG data, which are almost the same thing. But these are collected typically on patients that undergo surgery for various numbers of reasons. But one of the main reasons are surgery for epilepsy. So when they have resistant epilepsy, we can record their brain activity to try to map to localize the center of the epileptic foyer. And while we do that, researchers come in and also record some data related to stimulus for fundamental research purposes. So these data is, of course, very clean because you are getting signal that's much more precise from deep electrodes inside the brain or, really at the surface of the cortex. But as a trade-off, you can't really choose, where the electrodes are going to be and what you're going to look at because those are patients and they're here not for research, obviously. Anyways, moving on. So I guess we have covered that more or less, but basically, yeah. So you have this electrical current that's created by this, bipolar. I don't know how you call it. Bipolar activity, electrical activity along the dendrites. And so with these electrodes at the surface of the scalp, what you collect is for each of these electrodes that you have, and that's more or less what the EEG cap looks like. You're collecting a time series that reflects the temporal signal of amplitude, electrical activity amplitude across time. So just quick historical note. So that technique was invented or discovered, I don't know, back in the early 20th century. So that I think that was like the first paper is like 1924 or something, by this guy who I'm not sure his name is, Hans Berger, I think. I forgot. Berger? Okay. So yeah, and so that's very interesting and funny because basically these signals are exactly the similar, the same time that we look at today, and they're
much cleaner than what you see today.
Actually, yes. You're like, what? Well, the guy, to be honest, these people at the time didn't have like a whole network of subways around them when they were collecting their data. Here it's a bit more clean, and we'll get into that later, but it comes down to what I was saying about EEG data, which is basically you're spending most of the time denoising. And then once you are confident that you denoise enough, you can start analyzing. But yeah, that's pretty clean. So yeah, just for comparison, that's a full EEG setup back in the 1920s. And today we have obviously much more portable options, including here in the workshop. Not exactly those, it's another brand, but it's the same sort of, setup with like things that you can plug and play and then move around with it. So just very briefly, what you need to do is you need to have electrodes that you're going to put at the surface of the scalp in a way that doesn't move as much as you can. So that's why you need a cap or something like that. You need conductive gel to just help the electrical signal to be picked up better by these electrodes. You need, of course, an array. So you can't just have one electrode. You need as much, and actually the more the better, for a reason that we're going to see soon. And then you need an amplifier to be able to collect this data and then record it in a way that's going to be able to be then analyzed. And the sampling rate is usually 500 to 1 kilohertz, which means that the temporal definition is quite good if you want to go as high as that, as we're going to see in a few moments. So here on site, we have this set, which is, so we have the brain vision equipment, which has been loaned, which are not dry electrodes, hi Brett, which are wet electrodes, and are very, very well tested, very well known EEG setup that has been used in countless papers, so very reliable and good signal to noise ratio. And more there are, as you saw earlier, there are developments of more portable EEG setups, including this one that's actually very nice because it still has the full 32 to 64. Actually, do you have a 64? No, maybe not. 32 yes. Channels. Yeah.
But this one is actually cleared, FDA cleared, so you can use it in hospitals.
Oh, yeah. Oh, really?
Sorry, not this version exactly. They have a version, it's based on this, but it's not the one that y'all have there.
And it's used for like
20N, yeah.
for epileptic
Doesn't matter for
crisis.
That doesn't matter for them.
What? Okay, well, I'm in person. So yeah, so that's what it looks like. And what you can see is that it's basically more or less clean signals, and then you have noise in the middle of it. That's the type of topography that you have. So if you look at the activity across all channels, you can see whether the signal, the polarity, the positive and negative amplitude variations. Then, so the data is basically a matrix of time samples by channel. Actually, I'm going to grab my phone so I can check on the hour. Because I have a tendency to, oops, go too long. Okay. And the problem we have, that's what I was saying, is that that's the correlation matrix of electrodes. So basically, the electrodes are highly correlated together, which means that we don't have a good spatial correlation, because basically the signal is like, how'd you say, smudges, smears, or in different electrodes. So then the other problem is that we have a signal to noise ratio in EEG data that's that can be challenging. So basically we are trying to decode, hearing a sound in a bunch of data that's also related to not only noise from electrical activity around, but also just the electrical activity happening in the brain. And that involves so many other tasks than just paying attention to a sound. So it's like finding, how'd you say, a needle in a stack of stay. Then we have external types of noise. As I said, in my lab, for instance, at NYU, we have to deal with a lot of noise from the metro lines around. But here, even in a place that's somewhat isolated, we still have a lot of electrical noise. So we need to filter and apply a bunch of techniques. So basically, those techniques are to remove all those types of noise-related activity, either external or internal, such as also eye blinks and irrelevant things. Motion artifacts that are a big problem, because when someone moves or move their jaws, and yeah, there's huge things. And then there is also the irrelevant brain activity. So for instance, you see here that, people listen to a sound and that's what you're interested in. But then if they have their eye closed or their eye open, the signal looks completely different, but that's totally irrelevant to what you're looking at. So this is the sort of thing that you have to take into account. Those are glitches and slow drifts and things like that, other fun sources of noise that you have to take into account. So EEG analysis is basically various denoising techniques that you combine all together and you wish for the best. So the way now that neuroscience, we're going to go brief on that, but this just for, historical reasons and methodological reasons, the way we deal with this and the way people have looked at what the brain does in response to a stimulus is primarily through looking at denoising through averaging. So you present the same stimulus, for instance, the syllable, over and over and over again, and basically you trace the average response to this one stimulus. And so this way you have a response that's been averaged, the noise has been averaged out. And here you see appear some interesting, what we call EEG components that are brain signatures of certain processes corresponding to peaks in amplitudes in the EEG trace that's time locked. And because EEG is so temporally precise, on the order of 10 milliseconds, you're able to identify these components on the order of 50 milliseconds time window. You can see that this component is related to syntax processing, while this one is related to decision-making or semantic component or things like that. So that's why it's very interesting, is that because it's so precise temporally. So for instance, very famous paradigm, the oddball paradigm. So you have a steady stimulus that's always the same, and then you present something different. You have a neural marker attached to this difference that you can identify as a peak in amplitude at a certain time in the EEG response. So that's how EEG analysis has been done for 20 to 30 years, basically, isolating these components. Another type of EEG analysis is to look at the frequency over time analysis. So you do that through, Fourier transform, discrete Fourier transform, where you're going to look at the frequency composition of the signal over different time points. And this is interesting. I'm going to go fast here, but this is interesting. It has been interesting and useful to isolate frequency components of the overall brain activity linked to certain neural processes. So it's believed, for instance, it's established that binding information across sensory modalities is linked to a high frequency in the order of 30 Hertz brain activity picked up by the EEG. So you do that by looking at the difference between, for instance, congruent and incongruent types of stimuli from different modalities. And by looking at the difference, you can identify the time frequency windows that are markers of this contrast between these conditions. Another thing that's very useful, and I also wanted to mention it because it's been used here in Telluride to apply one of the first closed loop with audio decoding that we did, is phase locking. So phase locking is that when you're going to look at the activity in one frequency band, and you're going to look at how this brain activity is phase locked to the stimulus, and how this phase locking is consistent over time. And you can use this technique to, so here it was used, what was it used for? Yes, sorry, I haven't looked at that in a while. So here they were looking at high synchronizers and low synchronizers, and that was somewhat related to what? Yes. Okay, so people were asked to produce speech, and they found out that the people that were able to produce speech in a highly temporal coherence, like rhythmically coherent way or rhythmically precise way, also were showing better phase locking when only listening to stimuli. And that led to a whole theory about how the motor cortex and the auditory cortex are more or less synchronized together. And that leads to different types of people entirely. And that's why you have this bimodal distribution of high synchronizers and low synchronizers. And this person, Florencia Asaneo, who was here a couple of years ago, has a whole line of research on how that relates to different verbal abilities. And yeah, that's very interesting. So if you want to have a look, but it was also used to look at how people were paying attention to stimuli, and we used phase locking values to be able to identify whether people were listening to a stimulus going at a certain rate or another one going at another rate. And we use that to actually have people intentionally navigate a little car. So they had to pay attention to this stimuli to move to the left and this stimuli to move to the right. And so the closed loop was working, that we were picking up the phase locking, and then that was triggering the movement of the car. Okay, now we're gonna, just very quickly, we're gonna look at those decoding methods. They're mostly linear, and the reason why is that because EEG is essentially a linear combination of billions of microscopic events from synaptic events that are summed together and picked up by these electrodes. And that's why it sort of makes sense to denoise EEG using linear techniques, and we're going to see that it has been quite useful. So there are three main techniques that I'm going to present here, three main methods that have been, that have been used by people more or less related to the workshop or throughout the community of people looking at auditory decoding in general. And this is classifier, temporal response function, and canonical component analysis. And for each one, we're going to look into the technique, and then I'm just going to give a few examples or one brief example of how this can be applied. So the idea behind linear classifiers is that you want to test. Actually, I have time. It's until 11:15, right?
You started at 10:20, actually.
Okay. So, well, we'll have time for questions. The idea is to test at which moment a specific mental content or neural representation becomes decodable in brain activity. So you do that because you have the EEG signature, the EEG signal. That's a time series, for each electrode, you have a temporal series. And you're gonna look at each sample. So if you have, you downsample your signal at 100 hertz for 1 second, you're gonna train 100 classifier, and you're gonna look at how you can decode for each of these timestamps the neural representation as it's unfolded in space, so across the electrodes at one time point between stimulus A and stimulus B, for instance. So you're going to have lots of presentations of the two stimulus. You're going to record the brain activity, and then you're going to just, in a very simple machine learning typical technique, you're going to train the classifier on a certain set of data with labels, and then you're going to test it on an unseen set of data to see how we can predict the labels. Right? And by training the classifier, what I mean is trying to find the linear mapping that brings the best separability between the two neural representations at each time point. So yeah, that's basically this technique, and it's been developed in Paris by Jean-Rémy King and Stanislas Dehaene, 2014. So yeah, like more than 10 years ago. And it's been very interesting a lot of people I know use it for speech and phoneme decoding and speech representation and things like that. We're going to see a brief example later. But so basically, that's kind of reiterating, but you have these topological representations at different time points, right? For different type of stimuli. And so what you do is that you take for each time point, you take the topography between two different stimuli and you see how you can separate them. And if you do that over time, then you have like accuracy score or area under the rock, depending on what your algorithm do, but basically a decoding accuracy over time that's going to give you at different time points the ability to separate these topological representations. And what's interesting in the way they do it as well is that they can also generalize it in the sense that they can take the classifier train at one time point and test it for another time point, which makes you be able to see how well you can generalize the neural representation. Let's say, for instance, you have a phoneme that's being encoded. Can you use a classifier that was trained at the onset of the phoneme to decode it 100 milliseconds after? And what does that tell you about how the lingering of the neural representation over time? That's the idea behind temporal generalization. And these give this kind of graph. So the diagonal here is the train time, test time alignment. So you're training and you're testing at the same time point. And on the side here, that's where you look at what happens before, what happens after. And so this is a way also to see, for instance, how we anticipate, events. Like you can, for instance, I'm running analysis right now where I'm looking at how we can predict phonemes by testing, training the classifier at one time point and see how it predicts just before onset. And it works under certain circumstances. So that's very interesting. It shows traces of predictive coding, basically. So that's for this technique. And this has been used, as I said, in a lot of phoneme decoding studies. So these people, Jean-Rémy Kim and Stanislas Dehaene, they worked later with David Popple and his lab in NYU. And there was also Laura G. Williams there that did a lot of work about phonemic representations over time and things like that. And this is another person, Joan Orpella, from this lab that's looking at how you can decode intentions of speaking and imagined speech from the brain. So you ask people in the MEG to imagine that they're going to speak a certain syllable, and then you try to see if you can decode that from the brain, which is obviously very useful for a bunch of clinical applications. As you can imagine, people who lose their ability to speak, for instance, if you just can decode their intention of speaking, that's a huge win. And so yeah, so this is an image of one of his recent paper when he was decoding the syllables from just people imagining simple syllables, which were tapaka. And just as...
Sorry, I have a question.
Yes.
If I may. So these predicting what is latency? I mean, there's a delay between the actual and the, you know, and what the EEG says. Is that something you learn or is it fixed?
The delay in for each individual.
Yes.
So these, yeah, very good question. So these decoders are trained on each individual person. So the delay is going to be taken into account by that. And the way you do that in other techniques that are looking at the more like the how do you say, the traces or the impulse response, which obviously is affected by these delays as well, is also trained with lags. And so you account for that and you account for it at the individual level.
I see.
But also, it should be pointed out that these the delays are somewhat a bit different, and they are linked to interesting things such as the age, you know, like, you know, infants process things at a different time than adults, and it's actually a signature of certain neural processing for consciousness processing, for instance, that's relevant. And some are irrelevant, like for instance, you have more myelin, or you have a bigger brain, or you have a thicker skin, or no, that wouldn't, well, I don't know, you know, stuff like that.
Yeah.
You see what I mean, right?
Yeah.
And those are not relevant, they're just noise. But overall, the ERP research, so the way we analyze the peaks and amplitudes, tells us that we have overall, in average, a temporal precision and consistency good enough that we can infer mechanisms for most of the population. Yeah. Okay. So another technique that has been used, including by people here in this workshop, and that probably we're going to use this year again, is temporal response function. And the idea between the temporal response function is that the neural response can be described as the convolution of one stimulus feature or a set of stimulus features with a channel specific kernel. So what you do here is that you take a stimulus feature or regressor, and it can be the envelope, it can be phonemic information or phonemic surprise, if you have a model for phonemic surprise, semantic surprise, melodic components, pitch, you know, whatever, you name it. And you then train a kernel to fit, to better describe the response, the input-output response between this regressor and the EEG channel. And once you have trained this kernel to do that, you test it on an unseen set of the data, and you obtain a predicted EEG. So you take the feature, you take the convolution, and you predict the EEG. That's why it's a forward model. You're predicting not the stimulus, but the EEG. And then you take this predicted EEG and you correlate it with the actual EEG for this stimulus. And you have R values that are indicative of the cortical tracking. And I say cortical because EEG only records stuff that are happening in the outer, you know, the cortex. The cortical tracking of the regressor, so of your feature, envelope, phoneme, surprise, whatever you have put in as an input. Yeah, so that's pretty much it. Those are values that are indicative of the tracking. So, you know, you can contrast conditions, such as we'll see in a moment with music, but you can also do it with speech under different noise conditions, or understanding and not understanding certain languages. For instance, if you want to look at high-level things, so how you encode envelope if you understand, you know, English or French, or if you don't, these sort of things. You can also look at these the traces, these impulse responses, because they're glorified ERPs, if you want, or they're like a model denoised ERP trace. So the peaks and amplitudes are also going to be indicative of the type of responses that you have. They should look like somewhat ERP, auditory ERP. And yeah, so this technique has been used, I just want to mention, in a paper that was looking at how people encode very high-level feature of music predicted by a model, which is basically musical syntax. So we used a model to trained on a bunch of music to output the surprisal or information content linked to each note. So how surprisal the note is, given the overall context of the the corpus it has been trained on and the local context of what just happened before. And this way we had this feature, which was not the envelope, which was not, but like a high-level musical syntax representation. And we looked at how it was encoded in the brain by musicians and non-musicians. And we compared it with just a model where we used acoustical features. And what we were able to find is that we have a significant encoding of these.
Can you point where you see that? Yeah.
Yeah, so that means acoustical, and that's acoustical plus musical features. And that's the difference. And so it just shows that the musical features adds, how do you say? Explains more of the data than just the acoustical features alone. And then we were looking at the envelope tracking, so only acoustical and melodic expectation. So sorry, there's just many names for this thing, which is musical syntax, if you will. And we had some very good, very cool ECOG data. As I told you, that's when people come into for surgery with grids of electrodes on their scalp. So you have a very good resolution of where that happens. And so we were able to really look at where the melodic encoding was happening. And it was linked to secondary higher level order processing of auditory cortices in the auditory cortex. So yeah, that was this paper that used this very technique. I think, I thought I had another example, but this has been used for, phoneme representation, like phonemic surprise, for instance, under different circumstances. Giovanni Di Liberto uses this to look into signatures of dyslexic processing in these populations, or infant response to speech, or things like that. And yeah, and just, it's good when you have a continuous stimulus that you want to look at, the encoding of this continuity, and not just the response to a time-locked stimulus, which was what we were looking at before. Okay, canonical correlation analysis is another type of linear decoding, denoising technique that has been developed for EEG by Alain de Chevigné, Daniel Wong, and Giovanni Di Liberto, and probably other people I forget, but and including here in Telluride. And the idea is to apply linear transformation to filter two signals, to find the components in these two signals that both maximizes the correlation between them. Well, that maximizes the correlation between them. So the idea is that you have, let's say, one single signal here, one dimensional, that could be an envelope, that could be anything, and several channel signal on the other hand. Here it could be EEG data, but anything else. And then you're going to apply first a PCA to reduce the dimensionality, and a set of filter banks also to reduce noise and everything. And then you're going to fit this CCA analysis that's going to from these high dimensional data, pull out the components that are maximally correlated together, and gonna sort of like order them by amounts of correlation between them. So you're gonna end up with what looks like a PCA in essence, which is a decomposition of your signal into another set of components. But these components are gonna happen to both your signals that are coming from both ends, to pull out the two components that are maximally correlated together, as ordered like that. That makes sense?
You do this offline usually, right afterwards.
Yes.
And then, but do you run it online?
But no, well, very good question. That's gonna come. You can actually. So here, this is I can't resist because that's what I do. But this was done to decode attention during music in a music listening experiment. So we took the envelope and the neural signal, and we applied this analysis, and then we were able to decode the attention engagement over time. And we were able to see that this attention over time highly correlates with high-level markers of musical processing, such as musical tension, for instance, on these two classical music pieces. And we did that with both EEG and ECOG. So basically, it's a good way to decode auditory attention. Yeah, I don't know if you guys agree or with me or not, but it's an assumption that when people pay more attention to a stimulus, the stimulus is better represented into the brain. And that's essentially what has been done to enhance speech and noise, as we're going to see in a second. So here what they do is that they apply this technique online to amplify the signal that the people are listening to. So here it's not really like a closed loop because people are pointed to what, I mean, I guess it is, but they're pointed to what they should be attending to, and you will see that the signal from one or the other gets amplified as the neural signal is being picked up. And so you can see how this can develop into very useful technologies for hearing in noise, ed assistance. So yeah, concluding remarks. EEG is cheap, non-invasive, and has very high temporal definition on the order of 10 milliseconds. As pointed out, depends a bit of, with idiosyncrasies with different type of people, some that are relevant and some that are not relevant. EEG only allows to collect cortical activity, because there is no signal that can be picked up by EEG from deep structural signal. It's also true for MEG, as I said, the magnetic field that you can record with these much bigger machine that you need a Faraday cage for and stuff. There is a lot of work that is also done with other types of data, such as the Bolt signal from fMRI. And it's kind of a complementary approach in the sense that with Bolt signal, which is basically the blood signal that the blood that rushes to neurons that they get activated, the temporal trace of that is not very good. It's like very slow. So it's an order of the, 1 second temporal resolution, 1 second, 2 second. But it allows researchers to look at really, very precisely everywhere in the brain where things are happening. So it's also an interesting way. It has been used to also decode engagement over different conditions in auditory and other types of studies. So it's, I want to mention it. I don't work with this type of data, but it's interesting and complementary. As a conclusion, I guess, one may wonder, because there is a lot of claims about, future technologies of BCI that can read the thoughts and things like that. And as researcher, we could wonder, have we cracked the neural code, or are we on our way to do that? And so just, a definition of what a neural code would be, it would be a full understanding of how neural activity gives rise to perception, thoughts, and behavior, which essentially would be a complete input. So everything enters senses and our brain. Output, which is all the brain activity, if we could record it, mapping. That would be, the beginning to cracking a neural code. What we've done is that we've decoded specific features such as motor intentions, as we said with speech, or phoneme representation, or even, different states of minds, different emotions in well-defined tasks. And these high decoding accuracy don't mean that we have cracked a code. It just represent correlates, neural correlates that we can contrast and use, for BCI technologies, for instance, and that are also informative for advances in neuroscience. They can also, tackle fundamental research questions about the brain and how it operates, and how its stimuli are encoded. But it's all, I just want to put a little bit of a, cautionary note at the end here. And with that, I want to thank you.
Okay, so I'm going to get started. Hi, everyone. I'm Roger. And I'm going to do this session in sort of, I guess, two pieces. So the first thing is I will give you a bit of an introduction to how we go about designing asynchronous systems, right? And then I'm mostly going to do a demo, essentially. We only have a limited amount of time, so I'm going to do this, but what I'll tell you is there are, I think, about 20 plus hours of recorded video that's available that you can go look at everything in excruciating detail, all the little pieces I'm going to talk about today.
And the links are on the schedule in the abstract.
Okay, perfect. Thanks, Andreas. So what do I mean by asynchronous design? I mean designing systems that don't use clocks. So all the computation is driven by events, by data arrival, This shouldn't require a huge amount of explanation in this audience, so I'm going to skip what I would normally spend 15 minutes on. So if you are so actually, show of hands, how many people here are chip designers? Okay, so actually a lot. So when you design a chip, normally you've all been probably writing Verilog, right? Or System Verilog, or maybe even Chisel, whatever your favorite hardware description language is, but they all operate at roughly the same level of abstraction, with one major exception, but most people aren't using it, which is BlueSpec. But and at that level of abstraction, you're basically in some text-based language writing sections of code that you know are going to get turned into combinational logic, and sections of code that you know are going to be turned into flip-flops, right? And so by the very nature of the way you have to describe your chip, you have essentially already made a very large number of design decisions, whether you like it or not, right? So if you're used to thinking in that way, this is quite a bit of a change, because we're going to step up the level of abstraction significantly. So we're going to start out with a behavioral description, right? So you're all familiar with behavioral descriptions, but normally the behavioral description is actually at a pretty low level of abstraction when you're designing synchronous chips in Verilog. So let me give you a very simple. So the way we design asynchronous systems is we think about the entire chip as a collection of components, right? All those components, because they're going to be physically turned into some circuit, are all operating in parallel at all times. Okay, you can't stop that, right? That's always the case. And then they need to interact in some way. They need to exchange information. And we're going to do that information exchange through message passing. So what do I mean by that? I send you a message, and you receive the message, right? When I send you a message, I have to wait until you're ready to receive it, right? So I have two components. I'll say entity A that sends a message to entity B, right? These are two components on my chip. They're running in parallel. And the model is we communicate by message passing to share information from A to B, right? So here I'm going to send, let's say I send the number 10. I have to say that I need some name for this. This is a channel, right? If any of you are familiar with parallel programming, this is the same syntax. In fact, the syntax we use to describe the hardware is actually the first message passing programming language ever invented. Okay, so this dates from the 70s. We're using the same syntax. There's no reason to come up with a new one. People always ask me why we invented this new syntax. They're like, actually, that's not true. This is the first ever paper on message passing. It was written in the 70s. We're using the same syntax. So there's a communication link. That's a channel. I say send to value 10. Here I'm going to say receive into some variable v. And the interesting thing about this is, and this is where we start differing from standard software programming. When I send a value, normally in software model, you say, I send a value, it goes out, right? Like in the internet, I send a message, I send an email, it just goes, right? But if you think about what happens, if I send a value and I keep moving forward, then that value must be stored somewhere. Otherwise, it's going to be lost, right? So somewhere it has to hold it. Some place has to hold the value. And because that place has to hold a value, that means there has to be some circuit that implements state. Right? Makes sense. Now, I don't want, in my hardware language, I don't want to allow the user to create all this extra circuitry without being aware of it. Okay, so the model we use here is when I try to send a value, I have to wait until the receiver is ready. So a send will block until the receiver is ready. A receiver will block until the sender is ready. People are usually don't find that odd, right? That's normal. So essentially when I block, when I try to send a value, I wait. When I send to receive a value, I wait. And when the two ends are both ready to operate, then they both complete, both ends can move forward, and we get set to value 10. Is that clear? That's the model. Any questions about that? Okay. That's it. Pretty straightforward.
Okay.
Yes.
I mean, doesn't A need to know when B is ready?
A needs to know when B is ready. That's correct, right? So there is a channel that connects the two, right? So this send on 10 has to name a channel. So let's call this channel C. So this send is sort of indexed by C, if you write, and the receive is indexed by the same channel, right? So the channel
There's an arrow going back, I guess, right?
Like the channel is bidirectional.
well, yeah, exactly. So see, we are now, this is why I asked how many people have written Verilog, because everyone always tries to think about how am I going to do this at the wire level, right? So you can do that, and you can, if you stay at that level of abstraction, it's going to take you a very long time to design anything. So
so can I follow the question?
Yes.
To clarify that, because I think that's an important point.
Yeah.
So the arrow there denotes the initiator.
No, actually that's not right either. The arrow denotes the direction of data movement.
The direction there.
Who is the sender and who sends the value and who receives the value. That's it.
Okay, yes.
Okay, so this arrow is the normal arrow you'll see in any message passing programming language. Okay.
So
go ahead.
those components like A, it's not doing anything until like B is ready to proceed.
That's right. So when you're at the send, when I'm doing a send, right? So let's say I do, x becomes x plus 5, and I'll use the syntax. So this is the send. This is send x on C. That's the syntax. Okay. At the other end, in parallel, I could be doing something else. So I do this assignment. So both of this send will be blocked until this process gets to this. And this receive will be blocked until you get to here. Okay, that's how it works. So what would happen in this program is if this is the entirety of my program, I would start here. Actually, I need to initialize X. This is not a great program, but let's say everything's initialized at 0. I could do this assignment and this assignment in any order. I have no idea, right? Say synchronous. But when I get here, I have to wait. And so you kind of know that these two programs are going to be here. That's going to be synchronized. So that's how you know when things are ordered, okay? Because the synchronization actions tell you when two programs are at the same program point. Is that clear?
But they're in parallel.
Sorry?
They are in parallel.
They are in parallel, yes. This has to be in parallel, yes. Right, exactly. Makes sense? So all you know is these are not, I don't know when this happens. When I do this operation, I'm going to send the value of X is going to get assigned to V, essentially, and then they keep going. Make sense? Any questions about the model?
So when you write your source file, you write it like this?
Exactly.
With columns and parallels in between?
Well, you write it as processes, and then the processes, when you create a process, it's implicitly running in parallel. I'll show you the syntax exactly. Yeah. We actually also have a parallel syntax if you want, but most people who do that are usually creating problems, but we'll get to why. No. Okay. Any other questions? Okay. So the name of the game is to basically take the calculation you're trying to do and convert it into these pieces with inputs and outputs that exchange information, that cooperate to solve your problem. Very simple. Okay. So I'll give you a very simple example of how I would do an adder. So what's an adder? An adder is something that takes two input channels, I'll call this A and B, and produces the result on the sum, let's call it S, right? So at this level, so the level of abstraction I'm describing here is a message passing programming language. We call this language CHP, which stands for communicating hardware processes. We used to call it CSP. We used to call it CSP until Tony Hoare, who developed CSP, was upset. So we changed the name. We just did it to give him credit. It's basically the same syntax, but there is a difference. But anyway, which I can get into if you're curious. So we renamed it. So if you look at old papers before about 1997, I think you'll see CSP everywhere. And then after that, you'll see CHP everywhere. That's when Tony visited our group. And anyway, that's the difference.
Oh, yeah.
So this is based on CSP, which is the first message passing programming language. So you have two inputs and an output. If I want to do an adder, well, what is my adder? I'm going to receive inputs on A and B, right? So I'm going to say A question mark, you receive on A, A is a local variable, B question mark B. I've used a comma. Comma is also a parallel composition, okay, in our syntax, okay? So I receive these two, semicolon. Now I've received both values. I do the calc, I sum them together and I send the result out, right? So I do S bang A plus B. That's my adder. But now if I wrote this program does this and then terminates, right? There's nothing else to do. Well, with one entertaining exception, your hardware normally doesn't terminate, right? But what does hardware terminating mean? Nothing. I have to just power cycle the system to do anything, right? So typically hardware doesn't terminate.
And the semicolon is sequential.
This is sequential. Semicolon is sequential, just like a normal software programming language, okay? So I basically normally wrap this in an infinite loop. Almost every chip looks like, all the little pieces look like an infinite loop where you do something. And the syntax we use is, this is the infinite loop. For those of you who are wondering why we use this syntax is from a paper from the 1960s by Dijkstra. Okay, so anyway, this Dijkstra's got it command language. Yes?
One question for the, like, just to explain how the semicolon is actually sequential. So in this sequence of operations, how do you ensure that the S-bang A plus B operation only starts after A?
Right. So when we synthesize this into a circuit, there will be signals that make sure that both of these have happened before I start this operation. So that is handled by the logic synthesis process.
Does it use the same logic as the channels as you explained up here, or is this like a different primitive on a lower level?
No, that's all the same.
Okay.
A channel is a channel, yeah, that's fine. Yeah, there's nothing special about this channel versus that channel. Is that the question? I'm not sure I understood your question.
So there's also some sort of handshaking logic that happens or something in this level in here, right?
Yeah, so maybe I should just get into the next level in the next thing I talk about, since everybody is really nervous about how this really works. Yes.
I was gonna ask kind of the same question.
Okay.
What exactly does this infer? It's like you have the handshaking logic, like you have your additional, like
You have some math.
logic.
Yeah, that's
Are
it.
you inferring state here to like hold on S?
No.
Or it's kind of like inherent in.
It's inherent on the channel.
So.
It's inherent on the channel. You just said
Like
it.
a pure combinational block.
No, this is not going to be combinational because there's a semicolon here.
So you have some kind of state element, right?
There will be some state holding variable. Yeah, I mean, yes, exactly. I mean, a circuit that even waits for two inputs to arrive is a state holding element.
That's true.
There's one here. Oh, you want to go ahead? Go ahead.
I want to make a comment just to everybody that repeat what you said at the beginning, that you guys already tried to start thinking of this level of abstraction, the high level of abstraction, and a lot of the rest of it is going to happen automatically with his tools.
Yeah.
He didn't tell you that.
That's right.
So that syntax it ensures that it's waiting for simultaneously for A and B.
Yeah, well, it's not. It's simultaneous. It's parallel. So yeah.
So there's no priority.
There's no priority here. That's right. Yeah, exactly. Yeah. Sorry, there's a question.
No, it does the same.
That is a question. Yeah, there's no priority here. This is unordered. Yeah.
Like a join
Yeah.
statement.
Yes, exactly. Yeah. Yeah. Depending on your favorite language and terminology. Yes. Okay. So since people have been are so interested in how this works under the hood, so let's talk about what happens, how a channel is implemented. Maybe I'll talk about that. That will hopefully help a little bit. How you do this well? Well, we finally know how to do this well. The automated conversion of this to gates. I'll talk about that as well next thing. I'm not going to have time to explain how we do the full synthesis, but I want to at least give you some flavor for the key elements. Right. So I've drawn this as a unidirectional arrow. This is a channel, but I need to turn this when I want to build a circuit. I need to turn this into wires, right? Gates and wires. So this channel, by the way, nobody asked me. This channel has some bit width, right? So there's some bit width for this channel. Okay. And it turns out that there are many, many, many different ways you can implement this channel. The CHP is the same, but the circuits will be quite different. Okay, and different implementations are good for different reasons. There are implementations that are very good as in being completely robust to delays. Those are called delay insensitive implementations for channels. There are implementations that are very compact in terms of wire count. There are other implementations that are really, really good for throughput. Okay, so there are a number of different ways you can do this. Okay, so the channel representation can be changed based on your goals. Okay, we even have channel representations that are radiation immune, right? So things like that. So that usually adds a lot more wires, but that's okay. Going to space, it doesn't matter how much that chip costs. Everything like it's noise. Right. So anyway, so I'll show you sort of the two most popular ways to represent a channel. So let's look at channels without data for a second. Okay. You might wonder, why do I need a channel if you don't have data? Well, you may want to synchronize, right? I may want to know that you have reached a certain point in the program, and the only way to do that is through a communication. So a channel without data is very simple. Two options. Even here, there are many options, but here's the simplest one. Request and acknowledge. This is all probably familiar to you. This is ancient history. By the way, I should just tell you that a lot of this basic setup was actually used in the fastest computers in the world in the 50s and 60s. Okay, Manchester had a series of computers which they built, the MU5, the Atlas. Atlas, by the way, is the first computer with virtual memory. Like something, very important major computers all were implemented with asynchronous logic. So you do a handshake. So here is A, and here is B. By the way, since send and receive and there's no data are symmetric, I could also flip who's a request and who's the ACK. That's a choice. Okay. But let's just pick something concrete. So the wire labeled request is the side that initiates the communication. So it's an obvious thing. You all know a handshake protocol. Do I need to go through this, or is it everybody knows what I'm going to do?
Well, RS-232.
For example, right? RS-232. Yeah. VME bus. It's like millions.
Let's do it. Let's do it here.
Exactly. Request, I ACK, reset, right?
So it's always a 4-phase handshake?
No. So these are all options. So that's a 4-phase handshake. There's a 2-phase handshake. By the way, there's even a 1-phase handshake. I'm not going to explain how it works. Yes.
That means that you still have a clock somewhere, no?
No. All you need is some set of gates that can generate the signal correctly. That's it. You don't need a clock.
But if you have multiple bits.
If you have multiple bits, let's see how you have data. There's no data. This is pure synchronization. So let's add data. Okay. So you can, by the way, you can do this as 4-phase or 2-phase. 2-phase means when there's a transition here, there's a transition here, and I'm done. Right. So that's the 2-phase. You can also use one wire, then you have to drive it from both ends. So you can set the request high, and then the other end pulls it down as the acknowledge.
I square C. I square C.
Yep.
So that adds some data now.
Let's add some data. So there are, I'm going to show you, yes.
Before you add some data, I'm sorry. So this is completely combinational logic now? Or
no, there will be state holding gates, right? Because you're going to have to wait for the request probably. So there will be some, usually on every cycle of logic, there is usually at least one state holding gate, unless you have a ring oscillator.
It's a special logic circuit. Anyway, it doesn't matter.
Yeah. I only have 45 minutes. Usually I spend a semester. And even then, I'm only touching the tip. The class that I took at Caltech was a year, just for calendar.
Go ahead then.
Anyway, so there's request ACK. So the simplest way to do data that everybody understands in a very straightforward way is I'm just going to add n data bits. Okay. Now this protocol requires timing information, right? And the timing information is basically when I set the data bits. A different way, again, there are variations. The simplest variation is I set the data bits, and only then do I toggle the request. So when the request changes and I say, the other end is there, the data bits have to be stable. Okay, that's sometimes called a data bundling requirement. Okay, and this protocol is called bundle data. Okay, here, yeah.
So if there's any delay in the channel,
that's right.
Then
this has to be slower.
You add a little delay, a little gate delay.
That's what
yes, you have an upper bound of delay.
That's right, exactly. Right, so it's all of these are one-sided requirements. This has to be slower than that. Right, so you just make this, the easy way to fix it, which is not the best way necessarily, is to make this slower.
So then why is this called delay insensitive?
This is not delay insensitive. No, this is not QDI, this is not even delay insensitive. This is a bundle data protocol, but it's the easiest one for people to think about. Okay, this is not a delay insensitive protocol because I could add delays here and break it, right?
Oh yeah.
It's not delay insensitive. Okay. Now, if I wanted to do delay insensitive protocol, the simplest version is I'm going to use 2 N wires instead of N wires. Okay, and then I don't even need the request. Okay. So this is bit 0. I'll say D0.T. Okay. 2 wires for true and false. Initially, I'll just show you how 1 bit works. Initially, both bits are false. And I toggle, I set the true wire high to say it's a true, and I set the false wire to high if it's a false. Right? So at the receiver, it doesn't matter what the delay is, you can tell when the bit's there. And you know the value is. Okay. By the way, where does this come from? 1950s information theory, delay insensitive coding. There are books on this. Okay. And I just have a bunch of parallel things like this. Okay. So this has 2 N. But the other thing is I can use that as my request as well. Right. So I can get rid of the request, but I have 2 N data wires plus an ACK, right? So that's 2 N plus 1 wires for N bits. So that's costly. Yes.
So I don't see how this solves the problem.
How this solves which this solves?
Problem of the delay intensity.
Oh, okay. Well, here's the protocol.
Yeah.
I'm 0, 0. Okay. You're receiving the bit. You can add as much delay as you want on any of these wires. But if I want to send you a 0, you know unambiguously when I send you a 0. Doesn't matter what the delay is. Right? Make sense? Does that not make sense to you?
Just to clarify, so the receiver then makes sure that it has received either true or false.
That's right. And then it raises the acknowledge.
Yeah.
Okay, you can't acknowledge until you have received all the bits. So you wait for all the data to be ready. Then you raise the acknowledge. Yeah, so it's a full protocol.
There's a completion.
Right.
It's just like an AND circuit, completion circuit.
Yes, you need a completion circuit to generate the ACK, right?
Yeah.
You can't use timing. And then you reset, and then you reset. And that's the 4-phase version. There are 2-phase versions, et cetera, et cetera. Okay, is that clear? Makes sense? Right. So this is a delay insensitive protocol. Okay. So that's basically what ends up happening. But the whole point of what we've been working on is to automate the generation of all of this stuff so that we can synthesize all the gates for you, and you can stay at this level of abstraction. Okay. So I have 10 minutes left.
You can take a little more. It's actually fantastic.
So what's the next thing? The one next thing that you're going to talk about?
Oh, the next thing is I was going to show you the target language, what we turn this into eventually. Okay, but I can do that pretty quickly. So eventually I need to turn this into some circuit that I'm going to implement in CMOS, maybe other technologies. But I mean, I'm a big fan of CMOS. So my starting point is a behavioral description in this message passing programming language. You basically, what you will do is you will pick your protocols for your channels. So that tells you the wires that you need to drive on the interfaces. You'll take your X is variables and say, okay, I have a 20-bit variable, okay. I convert them all to Boolean variables. So the next step, which we always skip because there's no reason to do it because you know what to do and keep going. We convert everything to individual Booleans. So now all the variables in my program are Boolean. Each Boolean will be the output of some gate. And then the question is, how do we generate all the gates to respect what you wrote at the highest behavioral level? That's the idea. Okay. And so the target language we use is try to be as close to gates as possible. So this is my object code or assembly language. If you're a software developer, it's more like the assembly language for my chip design. And the syntax we use looks like this. So I'm going to show you a NAND gate. So this is a NAND gate with C at the output and A and B as the input. These are called production rules. Again, this is old terminology from programming language theory from the 70s and 80s. This says the way to interpret these rules is they all run in parallel. Okay, there's no sequencing anymore. All semicolons are gone. There are no channels. Everything is 1 bit. This says if this is true, then you fire the right-hand side. And this says set C down, lower C. This says if this is true, raise C high. Okay. So this is a NAND gate. A very popular gate is an inverting C element, which looks like this. And the thing that's interesting about this gate, so this says wait for A and B to agree and change the output. Okay, so if A and B are both 1, I set the output to 0. If A and B are both 0, I set the output to 1. Okay. But what's interesting here is now I have a state holding gate. Because if A and B disagree, C keeps its previous value. Right? So I can write latches like this. I can write anything you want like this. Okay. So I can write, basically, I can put, for those of you who like doing circuits, this is the pull-down network. Right? And this is the pull-up network. That's it. You just write the Boolean expression for the pull-up and pull-down.
But those two aren't the same, right?
Which two?
The NAND gate and the.
No, there's an AND here instead of an OR.
Oh, okay. Then I-
Yeah. Yeah. This is sometimes called a C element, inverting C element, Muller C element. Okay. So the question is, we go all the way from the behavioral description to a whole bunch of things like this. Each of these get turned into basically a cell, right? You find all the unique versions of this. This is where you do sizing, all your circuit level optimizations, fold things. Normally, whenever you have a state holding gate, we put a keeper or a staticizer circuit on it to make sure you don't have to worry. And that's it. That's how we build a chip, right? Yes.
I think it makes sense to me, like on the level of pull-out network, like you build your own gates.
Yep.
But there is no, so this is not compatible with like, normal static gates, right? You cannot use the standard AND gate.
Well, I mean, if you get a standard AND gate, you can use it.
Okay. Okay, so there is stuff that we can express here that is will not be part of
A standard cell library, correct?
the
Yes,
C element.
that's right. Yeah, that's right. Yes, this is richer than what you can get in a smaller. Yeah, go ahead.
If you have a completely delay insensitive design, how do you do sizing? Like, what's the?
It doesn't matter.
Okay.
So what you would normally want to do is, well.
You like a performance target.
Yeah, exactly. You would have a performance target, right? So that's what you'd use to drive the sizing, and then you'd minimize the sizes to meet the performance target so that you save on energy, right?
And is that included in like the automatic flow?
Up to a point at the moment. It's actually something we are adding to it right now. It's some code I was hoping to reuse, but I can't, so I have to rewrite it.
So we can do sizing and like change the drive strength if necessary.
Everything you can even do that in Act. Yeah, you can. So sorry.
Keep going. I think this is fantastic.
No. So in our hardware description language, we have enough expressive power for you to design these circuits at whatever level of abstraction you want, to the level where you can specify every NFET manually if you really want to do that. Okay. The system handles it all correctly.
You never look at this intermediate form, right?
We normally look at it when we are trying to like figure out like first time you have something that's new and it turns out that the standard compilation is inefficient, then we'll unpack this and go, okay, why is it bad? How do we make it better? Yeah. I mean, one way to think about it is we've kind of explored a very large set of possible, targets for the compilation, and we've already come up with some really good ones. So unless you need to divert from that, there is no reason to work at this level of abstraction anymore. Does that make sense?
Equivalent of like my synthesized netlist.
That's right. This is your synthesized netlist, exactly, right? Yeah, I mean, if you talk to people who used to do synchronous circuit design with full custom layout, I mean, there are lots of people still around who did that. They don't like to use the standard cell library. Okay, so yeah, you can do a lot better, but nobody has time. So you can view it as the same thing, right? It's like we give you some standard approach. You can use that. You might be able to do better by hand optimization. That's up to you. Any other questions?
I should point out that there's a lot of tutorials.
Oh yeah.
17 hours worth of tutorials in the links that we posted. If you want to go and learn details of more of this. So
this is like a very quick intro to sort of what we are trying to, how we go, what are we trying to do, and what's sort of the goal. So I mean,
You posted those tutorials on the NIC page?
Yes.
Or the website?
On the calendar.
On the calendar.
On the calendar, okay, cool.
Yeah.
On the abstract.
Oh, cool.
And so I'm going to give you a quick demo of like the tools that we have, to give you some flavor for what this looks like. We actually have documentation.
Good, let's see it.
So yeah, let's see it, exactly.
I'll erase this while you get that going.
Yeah.
Can you turn on the beam radio?
And I should suggest that if you're interested in doing like this, get involved with the project soon between now and the 11th of July, because that's the days that Rajit is going to be here, and the learning rate when Rajit is in the loop goes like this. If Rajesh is not in the loop, you will say,
100x.
okay? So,
So we have a session tomorrow on installing
Right.
the environment and the tools needed to run this village, so.
right, and Raj is gonna give a tutorial tomorrow on how to install the tools, where to get the Docker and get you going. So this is really, we are trying to get going on the practical aspect of that.
Whatever we are showing now, or that was you said, you can do it.
Yeah, this needs to be bigger. Huge. Okay, can you see that?
Let's take your laptop tomorrow and we'll be interactive.
Oh, yes, yeah. I think with all of your laptops, we will do like a practice session, run command one by one. So we will get all the environment will be set. And you can run the tests in those first.
Okay, so
Any Windows, Linux, Mac.
Let's see this here.
okay, so the first thing I'll just pull up is just the website for you to see, right? Actually, my name is weird enough that it's easy to find. You go here, you go to tools, but that's the Git link. You can go to docs. Okay, so there's actually there's a wiki with documentation, install instructions. We have a Docker container that has everything pre-installed.
Yeah, I'm referring to this. But
Yeah,
So let's
exactly.
look at the demo, actually.
Yeah, so let's just do the demo, exactly. So, shall we do the adder?
No, we want to process it.
You want a processor? Will you live with one instruction? Okay, so I'm just going to show you what the syntax of the language looks like. So let's just do a simple adder. Okay, so I have an adder, a process, def proc.
The back, read that.
Can you read that?
Not
Could you
really.
make it like a log?
Can you zoom it up?
Actually,
turn off the lights a bit.
The lights, I think. it-
also,
lights off the-
I can use a different terminal program with
Yeah, that's
with yellow. That should be easier to read. All right,
The opposite.
is that better?
Yeah.
No, just do it all.
How about that?
Just turn the lights off.
That's good, right? Yeah. Okay, cool.
Okay, let's go. Even I can see down here.
Now I can even see the.
So it was perfect before. It's everything off.
Top one in the bottom, I think.
Just go there, don't do anything else.
Okay, so F proc what?
Okay, so
Don't touch it, it's good, don't touch anything, it's good. It's all good.
so it's an adder. We had ports A and B coming in and a port C going out. Those are channels. Those channels need some data type. So I'm just going to say channel of int. Int by default is 32 bits. I have two input channels, A and B, and an output channel, C.
So the bank is the output and the question mark is the input.
Yeah, exactly. So those are ports, input ports, output ports. And then I'm going to need some variables. And then in this language, the way you do it is you say, this is the process described at the CHP level of abstraction. Okay, you can say PRS for production rules, the gate level. There are other languages as well. All right, so I'm going to receive A, B, C bang, A plus B, right? Right, very simple.
That's the infinite loop.
And it's an infinite loop right here, right?
It's fine, yeah.
That's the infinite loop right there. I can even write it like this if you prefer. All right. Straightforward. I mean, it's a normal programming language, so white space, C style comment, C++ style comment work. Okay, so that's my adder. Now let's say I want to test it. I'm going to import my file. Okay.
You're scripting.
I'm just going to put some source to generate some values. Okay. This is my test bench, basically. Right, I don't know, whatever. We have like standard sources and sinks, but I just want to show you the whole thing.
X, Y, X.
I'm sending 3 inputs, right? So those are some test cases, right?
0, 5.
And 17.
17.
All right, let's say X bang 3, 8, 7, X bang 2, maybe. I don't know. doesn't really matter. And then I need something that will receive the value and maybe print it out, right? It's case sensitive. So, and then the printing command is log. So in this CHP, in the CHP syntax, everything except log is synthesizable. You can also call C functions from here. So that's also not synthesizable. And the way you synthesize things is you erase all logs and then logs are ignored. Okay. Received.
So where can we call C functions?
Yes, you can. Yeah.
Inside the CHP? Or?
Yes, inside the CHP. There's a little extra glue you have to provide, but yeah. Yes. So for example, we have random sources that call the C random number generator and things like that. Yeah, that's all straightforward. We've even got a RISC-V core, which we synchronize with Spike to make sure that cycle by cycle, we have the same register file state, stuff like that. No problem. Yeah. Yeah, this language, this is not really a joke, it's true. We wrote this language to design chips, not to write papers. So it has all the things you would need as a designer. And if there's something that's not there, that's really important, we add it. Okay, so now I need to wire stuff up, right? So I think I had an adder, let's call it A. There's lots of flexible syntax for adding, for connecting things. I'm going to show you sort of the lowest level syntax. Let's do sync.
These are all instantiated.
These are all instances, yeah. So exactly. And now I'm going to wire things up. So I'm going to say A.A is, what is it? S1.x. A.B is S2.x. A.C is SNK.x. Then it's wired up. That, by the way, there's like tons and tons of syntax for connections, lots of different options. I'm just showing you sort of the lowest level one. Let's see if this just parses things. Could not find specified tab. Add. Yeah, the error messages are actually useful. I called it adder probably. Yeah. There we go. Fine.
Also the import, right? Oh, no.
So the file is called add.
Okay.
All right, there we go. So I can simulate this. Test is my top level process.
-P, okay.
P is the top level process, right? That's it. The warnings, I'll explain those warnings in just a second, but I can like run everything and we can see it run. There's actually help here. You can save a VCD file and plot waveforms if you want. There's all kinds of stuff here. You can get things, you can watch a channel. So for example, I can run the same simulation and say, I want to watch, what is it, A.x. Oh, right. Oh, that's right. In A, it's called A, sorry. Now, if I cycle it, you'll see all the state transitions on this channel. It said, okay, this is time, this is the instance name, and then this is the message, right? So it said, oh, initially I was blocked, but at this time I tried to send a value, okay? And so at time 10, A received a wake up and it got the value and it was woken up by process S1. So you can trace who woke up who. And then, you did a send. Anyway, so you can just see the whole, you can see the detailed transitions for every channel action, all the possible things that happen if you wanted to.
So this program, in terms of time, it costs 7 units.
10, everything is 10 units of time right now.
Yes.
In this by default.
70 units of state transitions.
That's right. Right. Yeah.
So that basically tells you how long you will run.
That's right.
Run.
So by the way, if you have a gate level design, Axum actually supports back annotation SDF.
Oh.
So that works, which is pretty nice. So you can get proper things. Anyway, so that's basically the CHP level.
And what do you do next then?
What do you do next? What do I do next is I'm going to turn this into a circuit, CHP to PRS. This is actually a bad version. We have a new version that's much better, but doesn't really matter. So let's do a bundle data circuit.
Well, this is how you define your protocol.
Yeah, so you tell the synthesis tool what protocol you want. So your -B is bundle data. So that uses the request ACK and data bus, right? You can say which logic synthesis tool you want for all the expression optimizations. I'll use ABC. And then I'll say it's test. Actually, I just need to synthesize add.act, right? And the process is called adder. And we call the output out.act. Okay, so there you go. So here's out.act. You really don't want to read this very much, but like you don't like to look at the synthesis output, but this is the synthesis output. There's some slick things in act. There's a notion of refinement. So the SDT_adder is a process that's an implementation of adder. But what that means is it actually inherits the CHP spec. So remember when we ran ACTSIM before? You got this warning. So ACTSIM can actually simulate the circuit at any level of abstraction. It even can do analog circuit simulations. So you can simulate it at the production rules, the CHP, or the transistor level. It links against Zeiss. That's how it does the analog simulation. And because it has this internal type system, it can actually synthesize the interfaces correctly. So you don't have to do anything. You do a mixed level. Yeah, Zeiss is H-Spice, basically, yeah. Okay, and that's what it's saying. It's by default, it does ask for the gate level to simulate. It usually asks for a more precise model. Doesn't say analog by default for obvious reasons. It's way too slow. So here it said, the default was PRS, it didn't find it, but it's substituting the CHP model for the process instead. Okay. Anyway, that's kind of how it works. So that synthesized one, you can simulate it at either level of abstraction by just by a configuration file. Okay, you can select it. That's it. So that's my output. Whoops. And by the way, what it did was it called ABC. So here is the gate level netlist. Okay, so it called ABC under the hood to run logic synthesis. So anything where we can reuse synchronous tools, we do that. There's no reason to reinvent the wheel. And so we can export to Verilog and import Verilog netlist.
Can you look at the top, go back to the very top. What is it? Does it give the interface at the very top of that more?
Oh, yeah, sure. Yeah. Right. So
module it's in.
Right. So
what is this language now?
It's still ACT.
Okay.
It's just that the interfaces now are Booleans, which are wires.
Okay.
Instead of channels. It's a lower level API, right? So here are all the bools. So the block I'm going to connect to is this one. Okay. This little wrapper we have for ABC for, I can get into why we need it for ABC. We don't need it for Yosis or Genus. So that's the block 0 has two inputs, which are 32-bit Boolean variables. That's standard combinational logic and a 32-bit output.
So you can do synthesis from here with any tool, commercial or non commercial.
Yeah, so we can do Genus, currently Genus, Yosis, ABC. By the way that works, it's all actually quite, the software engineering piece of this is actually I'm quite proud of. I'll talk your ear off if you let me, but.
And so the next step.
So for example, I don't want to see this, but there is an external synthesis library, which is a shared object library, and you just have to define an API on how to call the logic synthesis tool. And if you just give me the .so for your tool, I can call your tool. There's no changes to my source code. Okay, you just need a shared object library with a certain API. That's how it works.
What do you do next then after this?
Then I need to do place and route. And I'm way over time, so I'll just show you the script that we use. So the tool we use for doing this is we call it Interact for Interactive Act. Actually, my students came up with this name in 2010. That's what they wanted. We wrote this tool in 2022.
Since we're doing bundled data, how are we satisfying like that time constraint?
Excellent question. So the beautiful thing about this is all part of the type system. If you look at the standard ACT definition, this is a standard library, channel.act. There is a bundle data channel in here, the definition of the channel. And in the definition of the channel, it says there is a timing constraint. And because this is in the definition of the interface type, all the tools inherit those constraints. So when I run the simulation, if you violate this constraint, it'll actually give you an error when you run the simulation.
How do I get, like, if I have a new PDK,
yes.
How do I get like my gate delay information?
How do you get your gate delay information? Everything is in, there's a configuration file, which I didn't tell you, for different technologies, which has all of this information.
But we can actually talk about it when we install, yes. I think it would be nice to show complete.
I have a cell characterizer as well, so generates.libs for you, things like that. So yeah.
So can you place and route it?
Yes, that's what I was about to do. I'll just do this the dumb way. Did I pick the right output standard.ia? Out.act. Okay, that's my read. I'll explain how this works. So interact minus t sky 130L minus rep equals 1 standard. Oh, right. What did I do here? Oh, right. I think.
You need a tweak with Excel.
Oh, yeah, could not find. Oh, no, there's something wrong. Oh, standard.I. Oh, right. Right. I'm asking. I'm synthesizing.
Like with 100 times faster, but legit here.
Got act. Oh, right. I didn't actually import everything I need, right? So that's what I forgot. Oh, right. Let's see what I did. Sorry, I'm laptop SDG buffer out. Could not find standard. Very strange. Let's see if. Oh, I think I know what happened. This is sorry, this is my bad. 1 second. I have two versions of this binary, the old and the new. That's what we are running into right now. Sorry. Let me fix that. Standard cells.act. Okay. Bet I wonder if that's the problem. See if you do PRS. All right. I'll have to figure out something wrong on my install. Sorry, I have usually 3 versions of this installed. So let me see if this fixes it. No, it doesn't. Okay. Sorry, I'm not sure why it's doing this. XNOR 2X1. It's here. Okay. Sorry, something weird is going on here. I'll show you a different run, which I just did 15 minutes ago before I rebuilt stuff on my laptop. Sorry, I'm not sure why I did that. I'll debug this. It's a different directory. It's the same script, actually. I just copied it from here. Actually, this might also break. Oh, no, it's fine. There's a, yeah, okay. Right, so the flow assumes you don't have any cells. And if you don't have cells, it actually generates initial layout for those cells for you.
Brute force.
Yeah.
Transistor based.
Yeah, that's transistor level. It doesn't wire up the cells right now, but it places and routes them. So I have done many experiments with this flow with my students in my class. The stat seems to be roughly it takes you 1 hour per cell to finish wiring, because it's already placed all the poly and all the diffusion. And there's always enough space for all the contacts and everything is labeled.
And what's the output now?
So the output is a placed def. So I wonder what happened with the other thing. So let me just open K-layout. There's an out. Okay, let me just open. I'll show you I'll show you what the script looks like. I wonder what I just broke. This is industry standard def, right? We normally import this into Innovus to finish the layout. Okay. So here is the placed def.
Is that D to A converter?
No, this is just the placed def.
Oh.
The def file with all the cells and this has the power routing. This doesn't have the detailed routing. Okay, but it has all the power grid is connected. The layout, yeah. This is the layout.
This is the layout of your outer.
Of the whatever it was in this directory. I don't know what example I used. There's something I screwed up something. I have to check. But what I want to just tell you what I did. Right. I'll show you what the script has. Forget about this for a second. So I load the physical database. I read the synthesized file. I elaborate the design, I set the top level of my design, then I map the circuit to a cell library, right? So if you have a defined cell library, it'll match your production rules to the library and replace it. But if it can't do the matching, it'll generate new cells. And it'll tell you, here are the additional cells you need to do the layout. That's what it does. And then that just creates a placement region. This is a 1.8 bloat factor, right? So this is the placement density. 1 is the aspect ratio. And there's enough configuration information that I can actually generate the tech-lef. So that's what that output.lef is. This rect command generates the preliminary layout for all the cells that had to be generated. Dolly is our placer. This places the design. You have to tell it where the IOs go. Here it's on metal 1. And then this writes it to our physical database. And then we call the power routing. So this runs the power routing, does the reinforcement, all that stuff. And then it runs the global router. So it actually has something called output.guide. So it'll generate something called output.guide that is the global routing guide. And you can feed that to open source detailed routers like Triton Route to do the detailed routing. But I don't do that, but that's a separate issue. Yes.
How are you reading in the DRT rules to do like the template?
They're here. I have a simplified DRC rules.
So you're handcrafting this file basically?
Correct.
Every PDK?
That's right.
Are there any tutorials for how to do that?
Yes. It's right here in the documentation link. Here's layout, configuration file. So it says here are all the rules you need.
Rajat, I have to interrupt for a moment.
Yeah.
MPC group meeting is now starting in the MPC room. Everybody going to that, go over there now. Sorry, Rajat.
No worries.
Sorry for going over time.
But here, like this shows you what all the parameters mean.
Is this like generic enough to support like any PDK?
So I have used this up to GF12.
Gotcha, okay. Like dummy gates and all that should be fine.
Dummy, poly.
Okay.
So I think you guys, this is kind of this is a natural point to start any questions. So I think that this was kind of an overview, and to wrap up, to repeat what Rajit said, what we wanted to start thinking is algorithmically at the very high level, and the details are there to get your chip design or to do some synthesis, place and route, and this is really the process. And you saw in that directory there is multiple libraries. Obviously, Rajit that he designs and we're not, but
bye from here. Meet you over the MPC room.